Okay, hi. So we've got our second lesson on stuff to do with the extended practical investigation. Last time we looked at a few different concepts around scientific experiments, and one of those was on uncertainties, which, as we looked at, was a bit of a range in which you would expect your measurements to fall. You would express uncertainties in terms of, say, 5 plus or minus 1 as your measurements, and you'd be saying it would fall within the range of 4 to 6. 5 is in the middle of that, and you've got your range during which you expect your measurements to fall. So that's what we're talking about when we're talking about uncertainties, and that's the sort of thing we're looking at today. Now, just before I get into it, remember that you did an experiment at school where you had a cart rolling down a ramp and you did some measurements of that and you started working on a booklet, and I asked you to just get about a bit of that done before doing a different experiment, but we're going to be going back to that today. So you should be working through that once we've got through all this stuff, just because that's where this comes in, calculating uncertainties and also doing some stuff on lines of best fit and error bars as well. So those are all going to be popping up today. So first of all, when measurements are taken during the experiment, you necessarily make some approximations. So if I'm using a ruler, which has millimeter markings on it to measure the length of an object, I might measure its length as 15.6 centimeters. Now, that's an approximation because it might be 15.5 or 15.65. I'm rounding it to the nearest millimeter, the nearest 0.1 centimeters, and I'm going to say that it's 15.6 even though it might be off by a bit. So I've made an approximation just because that's the best that I can reasonably do with my ruler. I can only approximate the length of something to a certain, I can only say its length to a certain extent, and so the uncertainties are used to represent that. So since I'm rounding to the nearest millimeter in this case, which again is 0.1 centimeters, there's an uncertainty which is going to be half of that. It's going to be plus or minus 0.05 centimeters, and you can see that from the example. It's centered on 15.6. It might go down to 15.55. It might go up to 15.65. So from my central value of 15.6, it's going down by 0.05 or it's going up by 0.05. It's got an uncertainty of plus or minus 0.05 as a result of that. So when we take a single measurement using some instrument like a ruler or a stopwatch, we determine the uncertainty in our measurements by looking at the smallest scale that we use. So for the example before, just to repeat, I was measuring to the nearest millimeter, 0.1 centimeters, and so my uncertainty is going to be half of that. It can go up by 0.05 centimeters or down by that much. If it was going more than that, then I would probably up my value from, before I think I used 15.6, so I'd make it 15.7. So the fact that I've got my uncertainty says it's not going to be enough to go up by so much. It's going to be within the range that I've set. If I was not able to measure so carefully and I was measuring to the nearest centimeter instead of the nearest millimeter, my uncertainty would be plus or minus half a centimeter or plus or minus 0.5 centimeters. So just because the ruler's got that millimeter grading on it, if I'm not actually using that to take my measurements, then I'm not going to use that when I calculate my uncertainties. A different example might be like if you're doing some sort of projectile motion experiment. One person shoots a projectile and another person measures how far it travels away from the starting point. The person who's doing those measurements might not be able to use a tape measure and accurately record the distance to the nearest centimeter. They might record the distance traveled to the nearest 10 centimeters, for example. They might say it traveled 6 meters and 20 centimeters, 6.2 meters. They might not be able to get more fine measurements down to the centimeter just because of the nature of measuring things that way. So even though they've got a tape measure that goes down to the millimeter, they'd be using the nearest 10 centimeters, so their uncertainty would be plus or minus 5 centimeters, plus or minus half of that 10 centimeter measurement scale that they're using. So when you're doing an experiment, you've just got to think about the uncertainty based off how you're measuring it, how finely tuned your measurements are, and how finely tuned you can reasonably make them. Because if you're being overly ambitious and saying that you're measuring down to the nearest millimeter when really you're not, then your results aren't going to probably be as honest as they need to be. So that first way was one way of calculating uncertainties. It's the way that we use when we take a single measurement and there's an uncertainty associated with that single measurement. I measured how long something was. There's an uncertainty associated with me measuring that. A different way you can get uncertainties is when you have a few different values for the same result, and you average those out to get an average representation of what result you should have got. So my example on here is that I use a stopwatch. I measure 3 times, 3.0 seconds, 3.1 and 2.6. I average those out and I get 2.9 seconds. Now the method I'm going to use this time around is to find my uncertainty in my measurements. I find which of my measured values is going to be furthest away from the average value. So if I look at my 3 values, 3, 3.1 and 2.6, the average was 2.9. The one that's furthest away from that is going to be 2.6 seconds. So I'm going to say that for this set of values, my uncertainty is going to be the difference between 2.9, my average, and 2.6, the furthest from it. That's going to be 0.3 seconds. So I'd say that my average value is going to be 2.9 plus or minus those 0.3 seconds. My measured value of 2.9 plus or minus my uncertainty of 0.3 seconds. Now, those are the easy ways of calculating uncertainties. The next one's going to be a bit more involved, and when you did that experiment with the cart rolling down the ramp, you measured really a couple of different things. You measured how far it traveled, and you kept that about constant, so there would be an uncertainty in the distance that traveled that would be plus or minus half of whatever scale you used. If you measured the distance that traveled to the nearest millimeter, then it would be plus or minus half a millimeter. If you measured it to the nearest centimeter, plus or minus half a centimeter. That's the first way of calculating uncertainties. You also measured how long it took to travel down the ramp, and you did that 3 times. So when you find your uncertainty in the time it takes to travel down the ramp, you'll be using that second method for dealing with uncertainties, where you find the average and then find the value furthest from it and use those to get your uncertainty in the time to go down the ramp. The third one is going to be applicable when you look at how fast the cart was traveling. So that's going to be a bit more involved if you still have your sheet, which hopefully you do. Then when you try and work through those calculations, there's an example on the page about exactly how to do it. It's going to be similar to the example that I'm going through now. So what's happening is that I want to find the speed of an object, and to find the speed of an object, well, I use distance divided by time the way I always do when I'm finding speed. So my example is that I measured that an object traveled 15.6 plus or minus 0.05 centimeters in a time of 2.9 plus or minus 0.3 seconds. And from these distance and time measurements, I can calculate the speed using speed equals distance divided by time. So finding my value of speed is going to be pretty straightforward stuff. My speed is 15.6, my time is 2.9. 15.6 divided by 2.9, that gets me a speed of 5.38 centimeters per second. So that's easy stuff. Finding the actual value of the speed, it's easy. You just use your distance and your time. You don't worry about the uncertainties. But then I want to also find the uncertainty in my speed, and that's going to be a bit more involved. So to find the uncertainty in the speed, I'm going to first need to find the percentage uncertainties in the distance and the time. I've got my equation for percentage uncertainty there. It's that the percentage uncertainty in some quantity is its uncertainty, sometimes we call that absolute uncertainty, divided by the value that we've got for that particular quantity times 100. I'll show you how to use it on the next slide. So the percentage uncertainty for distance. My uncertainty in distance was 0.05 centimeters. My value for the distance that traveled was 15.6 centimeters. I take my uncertainty, divide that by my value, times by 100 to turn it into a percentage, and I get 0.32%. So my uncertainty for distance was 0.32% of my value that I measured when I did my calculation for distance, or when I measured distance, sorry. Similar thing for percentage uncertainty for time. The uncertainty was 0.3, my time measurement was 2.9, 0.3 divided by 2.9 times 100 gets me 10.34%. So that's my percentage uncertainty for my time. Since speed is distance divided by time, I'm not going to do any timesing or dividing for this particular calculation. Speed depends on distance and it depends on time. Even though they're being divided one by the other in my calculation, I'm nonetheless going to add together my percentage uncertainties in distance and time, which will get me my percentage uncertainty in speed. So I'm going to add together my 10.34 and my 0.32. That gets me 10.66%, and that's going to be the percentage uncertainty for the speed. So just to repeat, I got that by just adding together the two percentage uncertainties. Since speed depends on distance and on time, even though the equation is speed is distance divided by time, I'm still adding them together. That's just the process that we use. So what this tells me is that the uncertainty in the speed is going to be 10.66% of whatever my speed value is. And I know back from the previous slide that my speed was 5.38 centimeters per second. And I can do a bit of maths and figure out that the uncertainty in the speed is 10.66% of 5.38. And that's just going to get me out 0.57 centimeters per second. Just in case you haven't done your percentages stuff in a while, if I've got 10.66% of 5.38, what I put into a calculator is 10.66 divided by 100 times by 5.38. I turn my percentage to a decimal and then times it by the 5.38, or your green calculators have a percentage button, so you can just put in like 10.66% to 5.38 and that'll do the exact same calculation. Either way, it's going to get you 0.57 centimeters per second. So finally I can say that the value of the speed is going to be 5.38 plus or minus 0.57 centimeters per second. Now this picture doesn't have anything to do with the calculations I just did, but it's another concept that's being covered this lesson, and what we're looking at is about lines of best fit. So I've got 5 data points on that graph, and there's been a line of best fit applied to those, and that's a pretty good line of best fit. It's probably the best one. When we put a line of best fit on to a set of data points, the goal isn't to have it pass through as many points as possible. So you might think that, well, 4 of those points on my graph, they perfectly line up, and if I put a line on top of those, that would surely be the best one there. If only those 4 points were there and that little one down at 3 across 2 up wasn't there, then yeah, if only there's 4 points, that line going straight through them would be the best one. But because that 5th point is there, that means that my line has to be shifted down a bit in order to account for the fact that that point is there. I mean, if that point was really bad data, or if we didn't want that point, then we probably wouldn't include it in the graph. The fact that it's included in the graph shows that it's a point that we think is relevant and that we should include, and that means that our line of best fit has to be shifted down a bit from passing through those 4 points down towards the points that's below them. So it gets shifted down, I think like a 1/5 of the way down, might be probably a bit less than that. There's calculations involved that are a bit detailed, but the idea is just that if you get some data points and you need to apply a line of best fit, if they form a straight line through all the points, then perfect. But if you've got points all over the place, you don't just try and get a line through as many points as possible. You try and have it kind of in the middle of all the points that you have. So you want to account for all the points that are there, since they all do count, and they all need to have the line basically be as close to them as it can get. But lines of best fit, we don't get too involved in them. I think maybe in further maths you might, but not in physics, not in year 12. And the last thing, and my face is kind of covering up the graph, but not in any way that matters. I've got a graph there. I've just invented some numbers. I've created a distance time graph, and just as a little side note, when you make graphs, make sure you label your horizontal axis, make sure you label your vertical axis, and make sure you give it a title that represents what's going on. Normally when you give it a title, you kind of say what's going on and what your variables that are being graphed are. So you can see that on my vertical I had distance in meters and time in seconds on the horizontal, and for my title I've said distance traveled by cart versus the time taken, not just distance versus time, but also saying that it's the distance traveled by a cart. So talking about what the measurements actually are for. Like I said, I invented the numbers. They're not based off anything on previous slides, but assuming that was the experiment that I did, the same one that you did, and these were my data points, then that's the sort of title that I would give to my graph. And I just have to also remember to put labels for units on my axis, meters on the distance and seconds on the time. So when we're plotting points, we often display uncertainties on our graph using what we call uncertainty bars. You can see those bars on the graph. In the graph shown, I've got uncertainties for my time, and I've got uncertainties for my distance as well. Sometimes you only have uncertainty bars that go up and you don't have any that go across, just based off what the experiment's like. But for this case, I just put both of them on to kind of illustrate that you can get both of them. So for my time measurements, when I made this graph, I had that every single point had an uncertainty of 0.2 seconds. So if you look at the graph, you can see that the bars from each point extend to 0.2 to the left and extend 0.2 to the right. They're going across both ways by 0.2 because my uncertainty is plus or minus 0.2 seconds. There are some little lines on the end of the graphs which are just part of error bars. So little lines on the end of the error bars. So if you're looking at those, just keep in mind those little lines are on the ends of your error bars. It'd be nice if I could point to them, but I can't really. It looks like it's yeah, roughly on the end of like that one, and like roughly on the end of all the error bars. Just got those lines. There's the convention we use, so just don't miss out that they're there. For my distance measurements, I made the uncertainties vary from one point to another. Most years I try and get students to go through Excel and make these error bars and lines of best fit, which you can do very easily from Excel if you know how to do it. I don't know if we'll do it this year just because we're a bit more time constrained, and also I don't know how that's going to fit with the experiment. So maybe we'll run a lesson on this, maybe we won't, we'll see. But for now, what you need to be able to do is just read from these graphs, read what the error bars are and what they tell you about your data points. So you can see that each of the 4 data points has vertical error bars of different sizes. I think maybe the 3rd and 4th one have the same ones. Maybe I made the numbers the same that way. But you can see that the error bars can be different from one point to another in terms of their size if your measurements are giving you errors bars, like uncertainties that are different from one point to the next. So that's just showing you how these these error bars work. And like I said, maybe we'll go through a lesson on them. Maybe we won't. We'll see. So anyway, so what's happening today is that you should be getting that experiment sheet filled in, getting it finished. There's some stuff on there about lines of best fit and I think error bars as well. Have to double check, but predominantly what you're doing is uncertainty calculations. So that's what your focus should be. You should be getting through those uncertainty calculations in your sheet, just to get a bit of practice for how you actually do uncertainty calculations. Other than that, there are checkpoints questions for you to be answering, so please make sure you're getting those done. And I think that's basically it for today, so you just want to be getting on with those.